If you don't know how a hazardous material is going to react, how can you make an informed response? How can you devise a strategy, select the appropriate protective clothing, stage personnel at a safe distance, or set up the proper decontamination procedures? In other words, how can you protect yourself when you don't know what to expect? You can. Your response to an incident will be safe and successful only if you understand the physical and chemical properties of the hazardous materials you're dealing with. This knowledge provides the basis for your actions at the scene and is essential to your survival. The following experiments demonstrate several categories of physical and chemical properties and certain related principles. These include vapor pressure, lower explosive limits, vapor density, oxidation, water reactivity, air reactivity, pH including dilution and neutralization of acids and bases, polymerization, and cryogenics. The experiments you'll see were conducted by a chemist for demonstration purposes only. Do not attempt to reproduce these experiments. Many of the resulting reactions are extremely dangerous and can cause bodily harm and damage to the environment.
What evaporates faster, acetone or water? Let's do a little experiment here. I'll take some acetone, pour a few drops in this pan, and I'll take a small amount of water and pour a little bit in this pan. In a minute, we'll see which one has evaporated. Vapor pressure is the physical property that determines how fast a liquid evaporates. The vapor pressure of acetone is about 10 times that of water. The higher the vapor pressure, the more likely it is to evaporate.
Vapor pressure is an important concept for firefighters because it's the vapors of a liquid that burn. Vapor pressure indicates how quickly a flammable liquid will vaporize and as a result become a fire hazard. Vapor pressure also indicates how readily a chemical will contaminate the air. Inhalation of airborne chemicals, of course, is one of the most dangerous routes of exposure.
We take a look at the acetone that we poured in there. At 10 times the vapor pressure of water, it's gone. Take a look at the water, still present. Again, the acetone evaporated 10 times faster than water.
Vapor pressure is of greater concern when it involves a flammable liquid. The greater the vapor pressure, the faster the liquid evaporates. The faster it evaporates, the more vapors it produces, and the greater the danger of fire.
The lower explosive limit is the lowest concentration of a flammable vapor or gas in air that can produce an explosive mixture. What I'm going to do is to take a couple of drops of gasoline and put them into this container. We'll mix it around a little bit to vaporize the gasoline. And then we'll see if that's enough to ignite. You think that's enough vapor to ignite it?
There is an opening in the side of this plastic container through which an ignition source is introduced.
Nothing happened. The concentration wasn't high enough. We hadn't reached the lower explosive limit. Now what we'll do is take some more gasoline, build up some more gasoline vapors inside the container to try to reach that lower explosive limit. Remember what we did, each time we added a small amount of gasoline to the container, slowly building up till we reached the lower explosive level.
The lower explosive limit is a common reference term that's applied to certain hazardous materials. This limit can vary, depending on the chemical involved. Instruments are available for measuring explosive limits of specific chemicals. When you're responding to an incident that involves a potentially explosive gas or vapor, be sure to find out what concentration is necessary to sustain an explosion. This information, in addition to specifics on temperature, vapor pressure, and other conditions, will give you a good idea if and when an explosion will occur.
Vapor density is a physical property that tells us whether a gas or vapor will rise or sink compared to air. Some materials are lighter than air, some materials are heavier than air. If we take an example of methane, methane has a vapor density of 0.5 when compared to air, so it's less than the vapor density of air. It weighs less than air, so methane will rise in air. An example of a material heavier than air is propane. Propane has a vapor density of 1.5 compared to air, meaning its vapors will sink in air.
By confining a gas in a bubble, we can prevent it from dispersing in the air and more clearly show its properties. The methane used to produce these bubbles illustrates how a gas with a vapor density less than that of air will tend to rise. When enclosed in a room, methane and other light gases will move toward the ceiling or toward open windows and eventually disperse. Unlike heavier gases, they don't accumulate in the lowest area. The propane used in this next experiment shows how a gas with a vapor density greater than that of air will sink. In an enclosed room, propane vapors will accumulate near the floor. While both methane and propane are flammable, propane gas may be more dangerous in an incident because the vapors are less likely to disperse and tend to become concentrated in low-lying areas. Remember that heat and air turbulence, which are likely to be found in fire situations, will affect the tendency of vapors to rise or settle.
Another example of vapor density is to look at the heavy vapors created by carbon dioxide. It normally comes as in an ice form, but when we add water to it, it creates carbon dioxide vapors which will flow downhill. They're about 1.5 times heavier than air. We'll do that by adding some water to it, and you'll see that they tend to hug the low-lying areas and follow the terrain on their way downhill.
Heavy gases such as carbon dioxide can accumulate in low or confined areas and displace most of the air. If you enter such an area without your SCBA, lack of oxygen will cause unconsciousness and death. Because it displaces oxygen and is non-flammable, carbon dioxide is often used to extinguish fires. While the carbon dioxide gas has been made visible here by adding warm water to dry ice, remember that this gas, as well as most other gases, is invisible.
Oxidizers in general are materials that speed up chemical reactions, but by themselves they don't often combust. Here we've got a strong oxidizer in the pan in this crystal form. What I'll do is try to ignite it with a torch. You can see that the oxidizer itself doesn't burn.
Oxidizers are commonly used in industry to produce chemical reactions with other products. Although most oxidizers don't burn, they can, under certain circumstances, be just as deadly as explosives.
We just saw what could happen with a strong oxidizer and how even though we tried to ignite it with a torch, it wouldn't burn. Some oxidizers are strong enough that if you mix them with a fuel, will spontaneously combust. You need no outside source of ignition to start a fire. We have some same oxidizer we tried to ignite earlier in the can. I'll add some fuel to it and we'll see what happens.
Oxidizers aren't only prevalent in industry. Just about every home has an oxidizer in one form or another. The sodium chlorate in common household matches, for example, is a powerful oxidizing agent. In addition, most homes store potential fuels such as greases or oils. The oxidizer we're using in this experiment is a common pool product containing chlorine. You may have similar chemicals around your own home. Remember that in this demonstration, the oxidizer and fuel were mixed in exact proportions. A small change in these proportions could result in an uncontrolled explosion. Use extreme caution when you know an oxidizer is involved in an incident. Treat an oxidizer like you would an explosive, because under the right conditions, it is.
One characteristic of oxidizers is that they can provide their own oxygen to a chemical reaction. What we'll show here is we'll take some oxidizer, pour it in this can and ignite it. When we do that, we'll see that the ignition takes place and it starts to burn. But as the can fills up with ash and soot, it'll continue to burn even though outside air can't get down to the fire at the bottom. Again, that's because some oxidizers provide their own oxygen to a fire.
As this experiment demonstrates, an external supply of air or oxygen isn't necessary to sustain the reaction. Keep this property in mind when performing tactical maneuvers on an incident scene. Blanketing an oxidizer fire with a foam or other suppression material may displace air, but it won't necessarily extinguish the fire.
Some materials are very water reactive. One very reactive material is sodium. Sodium is normally stored either dry as it comes from the factory, or in use it's stored underneath kerosene or mineral oil. Sodium looks like a small chunk of Play-Doh. If we take a chunk of sodium and we throw it in water, there's an immediate reaction that occurs, the great release of heat and energy.
A fire involving sodium or another water-reactive metal poses unique problems because adding water just intensifies the fire. Research the physical and chemical properties of any hazard before you decide on the appropriate action.
Some materials spontaneously react with air. We call these air-reactive materials. What I have here is white phosphorus, and what I'm going to do is to take a stick of white phosphorus out and place it onto this warm brick. When we do that, you'll see the white phosphorus melt. The smoke that comes off of a phosphorus burn like this is phosphorus pentoxide. It's toxic and irritating.
Air-reactive materials like phosphorus are often stored in water or other liquids to prevent them from coming into contact with the air. Residue from fires involving air-reactive substances must be handled very carefully. If any of the reactive substance remains, it will reignite when it dries out or comes in contact with air again. Many air-reactive materials give off toxic fumes, so when dealing with any such fires, always wear the proper protective clothing and breathing apparatus.
The physical property of pH helps us get an idea whether a material is either an acid or a base. We know that the pH scale goes from 0 to 14. It's important to remember that from about 0 to 7, we call it an acid. 7 to 14, we call it a base. What we want to do is look at some common materials we have here on the table, and while I take a look at what the pH is of those materials, you guess at what you think it'll be. The first one that we have here is Drano mixed with water. We know that Drano is a very strong corrosive material. It can corrode pipes if it's not used properly. But what do you think the pH of that is? We check it with a paper and see that it's very strong, above 12. Next material that we have is tap water, water right out of the drinking fountain. What do you think the pH of that should be? We check it with the paper and see that it's pretty close to 6 or 7, what we would consider to be neutral. What's the pH of vinegar? Something you put on your salad all the time. An Italian dressing. Now we're all the way down around 2 or so. We take a look at some dilutions of acid. Here we have pure sulfuric acid, and what we've done is diluted it 1 to 10 with water, 1 to 100 with water, and 1 to 1,000 with water. Let's take a look at the pure sulfuric first. Way down, very low on the scale. We'll take a look at the pH of sulfuric acid diluted 1 to 10 with water. Do you think the pH will change much? Again, way down, very low on the scale. What happens if we dilute it 1 to 100? Again, way low down on the scale. How much water does it take to effectively neutralize or bring the pH of acid up around 7? Does 1 to 1,000 do it? Well, that gets us up somewhere in between about 3 and 4. actually can take quite a bit of water to neutralize or actually dilute an acid to a safer point. Now, when we talk about neutralizing, what we're trying to do is to bring the pH somewhere around 7. We'll do that. What I'll do is I'll take some regular tap water here and I'll mix in one of our stronger sulfuric acid solutions. We'll check the pH of it, and we'll see that it's very low on the scale, down around 1.
To dilute a strong corrosive solution by 1 pH unit, you'd have to add 10 times the amount in water. So neutralizing a concentrated acid or base by diluting it with water isn't practical unless you have a very small amount of corrosive and a large amount of water. When you're working with an incident involving acids, adding a weak base to the acid rather than diluting it with water is a more effective means of neutralizing the spill. Adding a strong base to a strong acid may result in an uncontrolled reaction.
What I'll do is I'll add some weak base to this acidic solution, and you may see it react a little bit. This is soda ash that I'm using. You can see it foams and bubbles just like vinegar and baking soda when you mix those together. Vinegar we saw was an acid, baking soda is a base. We mix that together, we let it react and foam up, and then we'll check to see what the pH is, to see if we've added enough soda ash to neutralize the sulfuric acid that was in there. We've added a couple tablespoons already, and you can see it really didn't make too much difference. We'll have to add some more. You can see I'm very careful about adding only a small amount of soda ash at a time, because it does foam up quite a bit. And that last bit I added, you could see that very quickly it reacted and the reaction was over with. That's one clue to tell me that it's probably pretty close to being neutralized. And I check the pH of it, and I can see that we're up around 9 or so. So we're pretty close to 7. What do you do when you have an acid spill? How can you minimize the hazard from that? You might think what you could do is to just dilute it with a lot of water. What we've seen earlier is that that doesn't really decrease the hazard. What you need to do is neutralize it using something like a commercially prepared material or something like soda ash or baking soda.
Corrosive spills are likely to cause severe injuries or property damage because most acids and bases are not only corrosive, they have other hazardous properties as well. Many are flammable, some are reactive, others are capable of oxidizing. When dealing with acids and bases, always keep in mind that you're likely to be dealing with more than one dangerous property. Don't attempt any action unless you know the possible outcome and you're fully protected against all the potential hazards.
Polymerization is the process of combining individual chemical molecules together, they're known as monomers, into a long chain of molecule known as a polymer. Those individual monomers are kept from polymerizing by the use of an inhibitor, which inhibits that reaction from taking place. When that reaction, known as polymerization, does take place, it can produce a lot of heat and a great expansion of the material inside a container. What I'm going to do is to mix a monomer together and take the inhibitor out so we can see what happens while the polymerization takes place. I've removed the inhibitor from this monomer. We'll watch and see what happens.
Think of a polymer as a chain and a monomer as one link in that chain. A monomer links up with other monomers to form an increasingly long chain. The resulting polymer is a different chemical with different chemical and physical properties.
While this polymerization reaction looks relatively harmless, what do you think would happen if we put it inside of an enclosed container? Polymerization is a reaction that can cause a great deal of expansion. When that expansion occurs, the container can fail.
Synthetic polymers are so prevalent in industry, their presence is taken for granted. Inhibitors are usually added to prevent or delay a reaction while the monomer is in storage or transit. However, inhibitors can lose their ability to prevent polymerization. Some are time-dependent, others are sensitive to heat. If an inhibitor loses its effectiveness, uncontrolled polymerization occurs. The results can be disastrous.
Imagine how much bigger the explosion could have been if this was a rail car rather than just a paint can. No, I'm not cooking my lunch. What I've done with those 2 hot dogs I just put inside that firefighter's glove was show you what can happen to tissue inside liquid nitrogen. This is a cryogenic material. It's a gas that's been compressed to the point where it becomes a liquid. Liquid nitrogen is one of the more common cryogenic materials you'll run into, but there's also others out there.
Liquid nitrogen and a number of other liquefied gases are shipped and used in large quantities in the United States. These cryogens are stored in insulated containers. However, some heat will enter and cause the cryogen to boil. The boiling produces gas that must be vented. If ventilation is blocked or isn't adequate, pressure can build up and rupture the container.
Now I'm going to take the glove out with the hot dogs in it, and we'll see what happened to them. The temperature of liquid nitrogen is at minus 340 degrees Fahrenheit. Let's take a look at what happened to our hot dogs. Imagine if that was your finger.
The experiments you've just seen have been performed under controlled conditions. At an actual hazmat emergency, you won't have the advantage of such control. You can, however, have the advantage of knowledge. Become familiar with the physical and chemical properties of the materials you may be exposed to, because those properties determine the nature of the hazard. Handbooks, special computer programs, and emergency telephone numbers currently available can provide quick and accurate information to hazmat team members. Understanding chemicals and knowing how to use these references under emergency conditions can help guide you through a safe and successful response.